Dr. T with a tutorial on implicit differentiation. Implicit functions are functions that are not solved for y. Two examples are given here. Number one is a simple equation of a circle, and number two is some more complicated expression. We could, if needed, solve the first equation for y so that we have y equals some function of x, and we could use our normal derivative rules to find the derivative of that equation. Solving for y in the second one is going to be difficult at best and possibly impossible. So we are going to be using something called implicit differentiation. The key thing to keep in mind when we take differentiation is how we handle taking the derivative of individual terms. For the functions we're using now, they're all in the polynomial form. So ultimately we'll be taking derivative of x to a power or y to a power. When we take the derivative of something with x to the power, we use our normal derivative rules. So we would multiply n times the coefficient in front of the x and then subtract 1 from the exponent. We need to keep in mind here when we take cy to the n that y is some expression of x. We just don't know exactly what that expression is. For example, we've worked problems where we had some constant times an expression, some function of x, to a power. To use that, we use the generalized power rule and the chain rule to take the derivative. We take n times c. We keep the parentheses as is, which is just y, is another name for f of x. We subtract 1 from the exponent, but then we have to multiply using the chain rule by the derivative of what's inside the parentheses. That's going to be f prime of x. Another name for f prime of x is dy dx. So just to summarize, if we take a derivative of terms with x's, we won't end up having any derivative notation at the end. And if we take the derivative of y terms, we're going to, after we apply the power rule, tack on multiplying dy dx. There are a number of steps in the process for using implicit differentiation for an equation. First, when we're doing something to an equation, we have to do the same thing to every term of the equation. So in this case, we will be taking the derivative of each term with respect to x of the original equation, including both sides of the equation. As we go term by term, left to right on the original equation, if we run into terms that have both x's and y's in them that are multiplied together or divided together, for those terms we'll have to use the product rule or quotient rule as appropriate. When we get to the point where we're taking derivative of terms that only have x's, as we said on the previous page, we just use our regular derivative rules. And when we have things that are powers of y's, we use the same power rule, but using the chain rule we have to tack on dy dx. After we've completed the process all the way across for both sides of the equation, we'll have some terms that have dy dx tacked on to the end and some that don't. We need to solve for dy dx. So all of the terms that have the dy dx, we keep those on one side of the equation, and by adding opposites we move the other terms to the other side of the equation. On the side that has the dy dx, we can GCF factor out dy dx and determine our leftovers, and then we can divide by those leftovers to get dy dx by itself. We may then be able to simplify what dy dx equals, possibly by factoring or by canceling if possible. The equation that we're going to work through is given here, and we are asked to find the derivative dy dx for that equation. In the process, the first thing said we have to go across the equation and take the derivative of each term in the equation. The sum and difference rule of derivatives says that we can take the derivative of each term of a polynomial that are added or subtracted together as separate derivatives. We also, when we take the derivatives, have to take the derivative of both sides. For this case, we have two things multiplied together, so we have to use the product rule. And for this case, we have a y to a power, we can use the regular power rule, although it's with a y, so we're going to be tacking on dy dx. And here we're taking the derivative of a constant, so we use the constant rule. When we take our derivative of a product rule, our shortcut that we use is we break the product into two things, u, which is x squared, and v, which is y squared. And under that, we take the derivative of each item. So the derivative of x squared, based on what we said in the tutorial, is just 2x. And in the overview, we talked about taking the derivative of terms with y. We use the regular rule for powers, but remember we have to tack on dy dx using the chain rule, because y is really a parentheses with some expression of x that we have to, using the chain rule, take the derivative of. To do the product rule, we will now cross multiply. So to get the derivative for this first part, using this table, we have x squared times 2y, so I'm going to put the 2 here and the y, dy dx, that's taking this cross, and now we take the other cross, we get 2xy squared. Now we have to go back up here, so we have minus, and the derivative of 4y is going to be 4 y to the 0 power, so that's just 4, and then we also, since we're taking the derivative of a y term, we have to tack on dy dx, equals, and the derivative of a constant is 0. I've scrolled up to give us more working space. The next step is to solve for dy dx. So any term without the dy dx, we want to get to the other side of the equation. So we do that by adding its opposite to both sides of the equation. That cancels out. So we're left over here with 2x squared y dy dx minus 4 dy dx, and that equals negative 2x y squared. Next step is both these terms have a dy dx in common, so we can factor out a dy dx using GCF factoring. My leftovers will be 2x squared y minus 4. Here we have dy dx multiplied by something, and we're wanting to solve for the dy dx, so the inverse, or the operation to undo, is to divide, so we divide both sides by 2x squared y minus 4. On this side, that cancels out, leaving the dy dx by itself. And we're left with negative 2xy squared over 2x squared y minus 4. Notice on the bottom we can GCF factor out a 2. Whoops. That's 2xy squared over 2 times x squared y minus 2. We can cancel out the 2's, and our final answer is negative x y squared over x squared y minus 2. Hope this helps you.